talk on queues with multi-type jobs and multi-type servers. Welcome.
Thanks. Thanks for coming. So this is quite an ambitious talk because I want to cover about 4 different topics, so I'll see how much I get through. I'm talking about multi-type queues. That means that we've got several types of customers and several types of servers. Okay, so servers 1 to k, and then we have some restrictions on who the server can serve. So in this example, there's 3 types of customers and 3 types of servers, or 3 servers. Server 1 can serve types A and B, server 2 types A and C, and server 3 can only serve type A. So you have these subsets of customers for each server. And at the same time, you can also see that A can be served by everybody, B and C only by a single one, and that's sort of every type of customer has a set of servers that are good for him. So that's described by this system graph, and I want to discuss this mostly under first come, first served policy. So one can think of 4 different sort of systems with this. One is a loss system where you've got just k servers, and every customer that arrives and doesn't find a suitable server is lost. And here we can find a reversible version of this. Then there's the standard queue when row is small enough, then it will be stable. And we can see that, and we get, well, maybe I'll get to that on the next slide. This might be relevant to internet traffic, this might be relevant to manufacturing. Then there's a model where it's overloaded, the system is overloaded, there's too many customers arriving, but they have only a finite patience, so they renege, and then you get a stable system. You've got reneging distributions for the different types. That's work of Talrea and Witt. And finally, I want to talk about infinite matching, which is just sort of thinking of 2 infinite streams of customers and servers, and they get matched on a first come, first served basis. So going over this again, that's the loss system. You've just got, say, 3 machines. These 2 are occupied, this one is free. That's the state of the system. In the stable first come, first served queue, what you will see is, because it's first come, first served, there will be just a line of all the customers, and the machines are sort of situated, moving along the queue. So this is the first machine, machine 2, it can serve types A or C. Then there are 2 customers here which cannot be served by any of the other 2 machines. They are waiting for this machine. Then machine 1 is serving either A or B, and then there's a few customers here which cannot be served by machine 3. They can only be served by 1 or 2, and then machine 3 is serving the first type A job, and then there's a queue of additional jobs that haven't been looked at by the machine. No machine has reached that far yet. Same system, when you add patience distributions, then customers also leave when their patience is finished. And finally, the infinite matching, you just think of the stream of customers like it's here. Okay, that's the first one, the second one, the third one, and so on. And stream of services, say, okay? And there's a service of type 3, a service of type 1, a service of type 2. And there's a unique matching between these. If you look at B here, he cannot serve type 3. That's the first one he can serve, so he will be matched with this one. This type 3, this server 3 can only serve type A, so it waits for the first one here. It doesn't matter whether you go from here or from here. You get a unique matching along these infinite sequences. I want to start, the way that I'll do it is I will start with this system, and I will talk about a property of global first come, first served that emerges. Then that motivates looking at this one. I'll tell you what we've done on this one. There's still lots of open problems, and then I'll go and talk about this system, back to this system, and tell you that I think this might help to solve something about the remaining two. So I'll start off with the overloaded system. So now we have, that's a different picture here. We've got 3 streams of customers arriving. We've got 3 pools of servers. The total service capacity is rate mu1 here, mu2 here, mu3 here. And these can grab either from here or here. This one can grab either from here or here. This is a sort of star-like graph with loops. It's quite complicated. And the way the service will go is whenever a server becomes free, he will look at the 2 queues which he can serve and choose the customer that has been waiting longest. That's the first come, first served policy. And then customers which wait more than their patience leave the system. The system is overloaded. There's this reneging. We're not, this is work of Talreja and Witt. They were not trying to analyze this as a stochastic system. What they did was to think what happens to it on a fluid scale. So that would sort of be when you use uniform acceleration, you just think of customers arriving at n times the rate, and you put n times as many servers in each of these. Then what you will get is that because it's overloaded, the servers will be busy almost all the time. The queues will force all the customers that don't renege before to more or less wait the same. They will approximately wait the same time, because one customer gets served and then the one behind him, if he didn't leave, he has waited just about the same time, because it's a very fast arrival rate. And eventually you get here that on a fluid scale you get first come, first served. So although these guys are getting served by different servers, say, than these guys, they still will have the same delay here and here and here. And you can then calculate, and then everybody will be waiting about the same time. Now, this is not a theorem, this is just the sort of what happens with the fluid dynamics of this. Yeah.
Sequences of service time they are equal in each queue.
Yes, right, I should have said that. I assume that the service depends only on the server. So it doesn't matter whether he serves here or here. That's the time he takes, and that's the rate of this one and this one. And then the time that they will wait will be exactly enough to sort of make the total rate at which people are served equal to the service rate. So this always has a solution. You start with a large W and you decrease it until you get equality here. And the question that Talreja and Witt asked was how many of the type, say, 2 are being served by these servers, and how many of them are being served by these servers. Let's call it Rij, the fraction of all customers that have Rij servers, or you can ask for the rate at which customers of type I get served by servers of type J. And to answer these questions, you first of all, you need to find your W. And once you have the W, then these rates, nu ij, must satisfy this set of balance equations, which just says that the total, if you sum up what gets served by J from all the different classes, that has to be equal. And also if you sum up what the total if you sum up over j all those j's which serve I, that has to be equal here. Now, these equations here, you can find the w. Once you have the w, this set of equations, linear equations, may have no positive solution. You need a positive solution to make sense. It may have a unique positive solution, and it may have many positive solutions. That's really the problem with this. And if there is a unique positive solution, then this will be the only possible rate at which this could happen. There's no proof that indeed there's any convergence to this, but this is sort of the values that the only candidate values. If there's another example which is simple, if you have a complete graph, if everybody can serve everybody, then of course the first customer gets served by the first server that is free, and it really just acts like a single, there's no, clearly you just get first come, first served, and then you would have that nu ij is just the is just mu I times lambda j or something like that. So Talreya and Witt could sort of discuss the service rates that emerge here for various types of systems. They couldn't solve a system like this because here, when you try to solve these equations, the solution is not unique, and they couldn't solve this one. This one we did later. I'll now this motivates going over to the infinite matching, where we can solve this, but this is still a mystery. Okay. Really about these overloaded systems, I think the point to remember is really this first come first serve, this global first come first serve that happens here. So now I go over to infinite matching. This might have also, this is also what motivated Witt to look at this problem, at least that's what he says in the paper. Ed Kaplan was looking at this in �84, and here is his story. Households that are eligible for public housing in the Boston area. When they apply for public housing, they're allowed to specify which housing projects they are willing to live in. And then when a public housing unit becomes available in one of the projects, it's being offered to everybody that, they look at everybody that is willing to live there, and they offer it, and they have to offer it to the one that has been waiting the longest. That's the rule. So that justifies the first come, first served. And one of the questions that he was interested in was people were sort of thinking, should they put in just their very favorite project, or should they put several projects in? What would make it their chances better? Or he was interested in that. But anyway, so here one would be interested in how many of the people of different types get assigned these matching rates of I and j. Other examples of this are adoptions, maybe kidney transplants, though that is a much harder problem with lots of, and maybe it might be applied to auctions, I'm not sure, but it sort of looks. No, here there's no queue. We are just thinking about really the idea here is that there will always, okay, the way that the story goes here is that there's always lots of applicants. Maybe they renege, maybe not, but if you just think of this, the model that I have here is really just to say that there's an infinite sequence of applicants. We will get to every one of them eventually, okay? And there's an infinite sequence of houses. But the thing is that it's not a queue where the server is busy, then he goes away, and then he comes back, which makes things much more complicated. This is in a way a much simpler model because there's no time. It's only really just looking at no time is involved. It's just the matching of these sequences. So, in fact, here is a more sort of let's say this is how the graph goes. So I'll define the problem more exactly now. You have this sequence of customers and sequence of servers, and each of the customers can be of one of the different types with probabilities given by a probability vector alpha, and they are IID. And similarly, the type of the server is IID from some probability vector beta. So the data of the problem is these vectors alpha, beta, and the graph. Okay? And then for every realization that you will have, there is a definite matching, and then you could look at the first n and see how many of the and what fraction of the n were I to j matchings. Okay? And you get those fractions for every I and j. And then the question is, does this converge? When does this converge? Almost surely to some value. And can you calculate that value? And this is and in a way, if you look at the at this problem, you have the same equations, but this was overcomplicated by those FIs, and there was the question of, does it really describe the real queuing system? Now we are just looking at the pure question of finding the matching rates. Okay? So what can we say about that? We again have those balance equations, which we also had in a different version for the overloaded system. A necessary condition to have non-negative solutions for these equations is that there is, I'll read it to you, this is the total fraction of customers of types in a subset C, and we need to have enough service fraction of all the servers that can serve C. The sum of their betas must be sufficient to serve all of these, and similarly this. In fact, this or this are equivalent conditions. This has to hold for every subset C or every subset S. And this condition holds, okay, and to prove that this is really the condition that is necessary and sufficient for a positive solution here, you look at the max flow min cut problem where you have the alphas here and the betas here, and you say that there's infinite capacity along all the, here you put the graph of the which customers get served by which servers, and you give that infinite capacity and you look for the maximum flow. If the maximum flow is 1, then you get, okay, any maximum flow of 1 gives you a feasible solution for this. And there will be a maximum flow if this holds. If one of these is violated, then you could have a cut which has less than 1. So that's a sort of, I think that's also Hall's theorem when you have just integers, right, for matching. Yes.
So when you calculate this ratio, what portion of what distance in this sequence you?
Okay, I mean, it's well defined for every n. I have these Rij's, yes. And then possibly they will converge. Okay, I mean the model here is well defined. It's IID alpha, IID beta. So there will be a sequence of Rijns, and they may or may not converge. I don't know. If they do converge, then those values Rij will need to satisfy these equations because because the fraction of alpha of i's in the whole sequence of IIDs will be alpha I. So, okay.
This theorem means that if this converges,
Then it must converge to something satisfying this. The trouble is that the solution, there may be lots of Rij's which are candidate solutions, and I have no way of choosing between them. That's the difficulty of this problem. Also the question, of course, whether it converges. So it's really those two questions. Richard?
No, that's right. So the question is, which thing does it converge to? And
Yes. I mean, if I can show that.
It depends on the fact that these are Bernoulli sort of things that you pick, right? Because if they came in some sort of more ordered stream.
Oh, yeah, that would be a different story. I think that's what you asked yesterday.
Or if you decided not to take the first match, you could also
Right.
make other matches.
Yeah.
And other sorts of matching could still have to satisfy these conditions.
Yes.
So
Yes, anything that would converge would. Yeah, so.
if you're taking first matching against Bernoulli streams,
Mhm.
particular set of algorithms to take.
Hopefully, yes, and I'm interested in finding what they are because they make sense. I mean, like in the housing example.
Okay, you're going to tell us more about this.
Yeah. So how do you? I mean, really, those apart from these equations, that's as far also as Talreya and Witt got. There's not much you can say at the moment. You need to somehow really use the stochastic thing, and this is how you can do it. You can get a Markov chain that describes what's going on here by just looking at the matchings of successive servers. So the first server will look down the lines C1, C2, etc., and take the first one in the line that matches him. So he leaves behind a geometric number of unmatched customers of all the types that he cannot handle. Then the n+1st server will first look at those customers that were left by S1 to Sn. There's some customers that they could not pick up, okay, and then he will look at those which were left by S1 to Sn. If he finds a match among them, then he takes the first one, and then he leaves one less behind for the next server. If he doesn't find a match, then he continues along the infinite sequence and will go and add a geometric number to the unmatched ones before he gets matched to, okay, before he gets his own match and sort of leaves. So Xn would be the Markov chain of ordered unmatched customers that servers 1 up to n left behind. So it's really the state space is more or less, you could say, words in the alphabet of customer types 1 to capital I. And it's easy to see that it's a Markov chain. I mean, really, this description that he, okay, that he either finds a match or he adds a geometric number, and we conjecture that this Markov chain is ergodic if and only if for every subset S and C which are not empty or the full sets, you really have those inequalities we had before as strict inequalities. If this holds, we conjecture that the Markov chain would be ergodic. We have no proof.
So we only have Arnstein's.
No, the only was kind of was equality. Well, I don't know. Yeah, I mean, okay. Now, if this Markov chain is ergodic, then you would have that Rijn, which is just a property of which is just something that you calculate along the Markov chain, would indeed converge almost surely to some values. So these values would exist. So now that's almost as far as we can go at this point. We have the conjecture. We don't know how to prove it in general. And suppose you can see that something is ergodic. We still don't quite know how to calculate this, except we can look at special cases. If we can find special cases where we can analyze this Markov chain, say, and find its steady-state distribution, then it is ergodic. And then from the steady-state distribution, you can calculate these these Rij's. Okay? Or at least if you can't get the steady state distribution, if you can prove that it is ergodic, then at least you know that the Rij's exist. So let me now show you the one case that we could really solve, and that's a case that nobody knew before. Okay, so here we have, that's the picture that I showed you before. There's three types of customers with probabilities alpha 1, 2, and 3, and three types of servers, fractions beta 1, beta 2, beta 3. Each server can serve all the customers except one, so I might as well, to make it simple, say he can serve everyone that has a type not like him. You can also, and this is not just for the 3, but for any I, and you can also add a type 0, with type 0 matches everybody. So those have no problem, they never queue up. Now these we can analyze, because if you look at the process of leftover customers, okay, you look at the word that describes the process X, this word will be composed of just a single type of customers, because you could never have two customers of different types that were left over by somebody, okay? And nobody would leave, okay? Everybody can serve almost all. So all the previous servers would not leave two customers of different types. So you just have, so instead of a word, you just need to say in this process X, what is the type that is sort of queuing up and that are left over, and how many of them there are. So it's a Markov chain that is really moving on the axis of the integers in dimension I, and you can get its steady state distribution, and it's this geometric, and you can get the formula for the Rij's, which I put here, and you can look at it. It's really neat. It's got all the I's and J's, and it's very symmetric, and okay, that's sort of, here it's alpha I, alpha j, 1 minus alpha I, 1 minus beta j, minus alpha j times beta I. It's sort of nice flip.
This just comes from analyzing the Markov chain.
Yeah.
Is it a reversible Markov chain?
I should think so, yeah. I mean, in this particular case, I don't know whether. Yes, I think so, because once you get to the 0, then you get to the. I'm not sure. We'll get to some. Okay, here is a different one. This is a double N model, we called it. And here we sort of, the condition for ergodicity is that, in fact, here you can immediately get the rates, because beta 3, type 3 here, these guys, the rate up here is just beta 3. The matching rate between 3 and 1 is just alpha 3, which must be less than beta 1. What's left over of beta 1 is the matching rate here, and the matching rate here, and this one is the leftover. And the condition for that to be non-negative is written here. But if you try to look at to sort of prove that really things converge to those values, then you need to analyze the Markov chain, and it's much more complicated. This is some sort of state description with transitions, and there's these geometric jumps here, and we definitely couldn't get a steady state distribution on this, but we could get a Lyapunov function which proved that it's ergodic. So for this particular model, I can say that I got the Rij's directly, and I prove by the ergodicity that indeed it converges to that. That's as far as this goes at the moment. So now now I will describe, okay. Here is now, so so the stochastic system didn't sort of. It's still very puzzling that for something like this, that you really need to go through this whole Markov chain to get those rates, or at least, I don't know, maybe not. So there were several attempts to try and guess what these Rij's are. So this is one algorithm which Caldenti-Kaplan thought it was correct in 2002, and then Kaplan came up with another idea, which is quasi-independent cells, and that's another way of calculating Rij's or candidate Rij's, and they both of them fail. I mean, this one was okay with the algorithm of Caldenti-Kaplan, but not for the quasi-independent, and this one was okay with the quasi-independent, but not with the Caldenti-Kaplan, and this one we just checked by simulation. Okay, and that's so.
No one has a way of guessing what these rates really are.
Right. Mm-hmm. Yeah, yeah. And Kaplan was thinking of things like you open taps, you've got all kinds of feed into a hydraulic system, and then you open taps, and somehow the water mixes and the water more or less flows on first come, first served. And there's some empirical formulas for that. Nothing really came from these considerations. So, okay, so now I'll go to the queuing system. And okay, so now it's no longer the infinite matching. We're now looking at a queuing system. This is a sort of N model. So customers of type A can be served by machine M1 and machine M2. Customers of type B only by machine M1. So machine M1 can serve everybody. Machine M2 only works on type A's. Arrival rates lambda A, lambda B. Service rates mu1, mu2, and now we have a queue of customers waiting to be served. And there's one more parameter that we need to describe this system, and we are assuming that everything is exponential Poisson, so memoryless, so it's Markovian. But there's one more parameter, namely what happens if type A arrives and finds that both servers are idle. The system is empty, okay? And then you need to specify what he does, whom he chooses, and it's specified as he chooses M1 with probability eta. Okay, so we've got the 5 parameters, lambda A, lambda B, mu1, mu2, and eta. This system was analyzed by Foley and McDonald and Ivo Adan.
To which server you will send?
Okay, so actually here are all the different states. The system can be empty. If the system is empty, wait, yeah, no, I'll go through the different states. If the system is empty, type B arrives, he goes to M1. Type A arrives, he chooses randomly. Then you could have the situation where this machine is working on a single customer in the system. If somebody arrives, he immediately goes to this machine, which is free. Then you have the situation where this machine is working and this machine is idling, because although there's customers in the system, they are all of them of type B. Okay? In that case, what can happen is when new customers arrive, if they're type B, they queue up. If they're type A, the type A that arrives will immediately go to M2, right? And the other thing that can happen is that this one finishes his work and then he takes the next type B, which was waiting, okay? And it's first come, first served. And the other situation is both machines are working, and then you would count, first of all, how many type B customers are waiting because they could not be served by machine M2. And then there's an additional x minus 1 customers which are waiting for beyond machine 2. So machine 2 hasn't looked at them yet. Maybe I need, I think I'll skip a little bit. And okay, it's this sort of description. You have a machine working on the first in the queue, because the first in the queue always will have somebody working on him, because if all the machines are working somewhere here, that cannot be, because this one has been before, so he would be served. First come, first served means that the first customer in queue will be worked on. Then you will have customers here which are waiting because none of the other machines can serve them. Only this machine can serve them. They are uniquely served by machine 1. Okay? Then you would have machine 2 working on a customer, okay, which it can serve. And then you would have some more customers maybe waiting here, which can only be served by M1 and M2, so none of the other machines can serve them, so they're waiting in here, and so on, until you get to the last machine that is now busy, say machine K, out of all the J machines, say, is working on a customer here, and then you've got another queue here of customers which, if there's still some idle machines at the side, they cannot serve any of these. If all the machines are busy, then these could be any customers that, okay, that's the way that the queue goes. And every time a customer arrives, if there's a free machine, he joins, he goes, okay, if there's a free machine, then he will choose randomly one of them, okay, one of the machines that can serve him. If there's no free machine for him, then he will just queue at the end of the queue. And when a machine finishes work, it moves along the queue until it finds somebody suitable. Or if nobody is suitable, then it becomes idle. Okay, is that clear? Yes, there's only one queue. That's
In this picture before you had two queues.
no. This is okay. I may be in the picture, but their queuing may be in different. Yes. So when I go back here, yes. So here you have. I put them as if they are in different queues, but really every time a machine becomes free, it chooses the one that has been waiting longest. Okay, that's really the idea. Foley and McDonald analyzed this and found asymptotic results, exact asymptotics with exact values for a constant here and geometric rates. And these are the natural rates. That's the total arrival rate over service capacity, and this is just the arrival rate over service capacity for these type B, which can only be served by this one. Okay, then they also discovered that for this system, if you choose eta as a particular value, then you get a product form solution. This is the exact formula from their paper. And this is the sort of state space description and all the transitions that can be solved if you put in this value of eta. Any other value of eta does not have a product form solution, but there's one value which does have a product form solution. And the next thing that I will tell you about is really that this can be generalized to any number of machines, and that was done by Jeremy Wishers, who was a student of Ivor Dunn in his PhD thesis. Eventually there was a hole in his derivation, so it waited for a while, and then the hole was plugged, and now we're sort of writing the whole thing up. So that's sort of how I am associated with it, really writing it up now. But before we go to this, to the generalization to any number of types here and any number of machines here, I will tell you a little bit about the loss system, which I mentioned. Okay, so now I'm looking at J servers. They work at exponential rates. Several types of customers arriving, Poisson arrival rates. There's a graph which tells you which types of customers get served by each of the machines. And this is a loss system. So whenever a customer arrives and all the machines that can serve it are busy, then it gets lost. So really the system is described by the set of busy machines. If I tell you which machines are busy in this exponential Poisson situation, that tells you the state of the system in its Markovian. And so if you are in this state, what can happen? Either one of them completes service. That happens at this rate. Okay, one of those machines, say the case machine, completes at this rate. And the other thing that can happen is that you have an arrival, and this arrival chooses, okay, from this state, chooses machine. Okay, these are the busy machines, there are some free machines, and there's an arrival which, when he sees these machines are busy, he just happens to choose machine MK. So lambda MK is defined as the arrival rate at which customers that are arriving of all the different types, the ones among them that can be served by MK, if MK is free, might choose it, and this is the rate of arrival, and it's defined by saying with what probability does customer of type I that arrives at rate lambda I choose server MK when he sees that these are the busy servers. Okay, so these things, once you have these things, you sort of know how the system works. And let's sort of play around and say, could this system be reversible? Okay, your question. Okay, could the Markov chain be reversible? Let's assume it's irreversible, then it must satisfy detailed balance. That is, all the departures, all the completions at MK balance with the MK getting free and MK getting busy would balance. And then you would have these detailed balance equations from which you can solve and get a steady state distribution, which is just like the Erlang loss system, except that it's different lambdas here and different mu's, right? I mean, it's very simple. Okay? No, it's not. Well, so if it would be reversible, and then you would be able to calculate the steady state distribution. And the question is, does this make sense? Well, it makes sense if this expression here on top is the same for any permutation of the machines. Okay, if this really is the same for any permutation of the machines, then this satisfies detailed balance and therefore satisfies the equilibrium equations and is the steady state distribution. For this condition here asks for lots of things, and it turns out that it's sufficient to really uniquely determine what these lambda MKs are. So the lambda, if S is a set of busy machine and M is a machine which is not busy, lambda MS will need to be this expression here. It's summation over those that cannot be served by the busy machine, that can be served by one of the non-busy machines, and it's just an expression. Okay, and now the question is, can you really find those assignment probabilities, those probabilities with which type I chooses machine M when it arrives and sees that S is busy, in such a way that you'll get lambda MS which is this. And it turns out, yes, you can always find those assignment probabilities again by solving this same kind of max flow problem. And this again may have several solutions because these lambda MS's need not, I mean, these are unique, but the P's may not be unique. Okay, but it doesn't matter here. In any case, you will get then the product form solution. So there is always a choice for the customers arriving, how they choose the machines, how they choose the machine that they go to, depending on which busy machines they see, which makes the system reversible with this simple steady state distribution. Whether it's useful or not, I don't know. It could be a good question to ask whether it has any good properties, right? This sort of assignment. I'm not sure. And from this, we can go and look at the queuing system. And this is what was in Wisher's thesis. And we're writing this up now. So this is the state. Okay, first come, first served. So this system has the discipline of first come, first served in the sense that every machine that becomes free goes to the earliest customer. And random assignment, a customer of some type that arrives chooses which feasible machine to join according to which machine he sees are busy. Okay? And it turns out that this can have a product form solution with exactly the same form of lambdas here. Then there's all the mu's here. This is more like the factorial sort of term, right? 1, sum of 2, etc. And product form here. And this is for every, so the state here is described by telling which machines are busy and how many customers, in what order, okay, a permutation of busy machines, okay, and how many customers are waiting between the machines and at the end of the queue, and the steady state probability of this, the stationary probability of this state is given by this product form geometric type expression with the alphas like this. And all you need is really that the choice, the assignment choice, will be the same as for the loss system. Okay, so that was the part that needed to be checked in this thesis, and that's the new part that we know that we can always do this. So there's always a product form solution like this. Now, that's all that we know. But now there's some ideas that we're still thinking about, working on, and that sort of. So first of all, in the derivations of this loss system, it looks quite similar to Erlang loss system. We suspect that it might be insensitive. Okay, I think Frank thought so too. So need to check that. Now the model, the queuing model was the first come first served. If you look at the lambdas and mu's, and you really in the expression here, oops, what happened to I want to go to the end. Okay. If you take out a common factor from all the lambdas so that what's remaining adds up to 1, and similarly from all the mu's, you get a sort of rho to the power of everything in the system. And that is sort of standing there. And then if you only consider the states where everybody is busy, you more or less get a description of the infinite matching problem. So we think that we can use what happened here to get some sort of product form description for the infinite matching. That's very hopeful. We think that might be the case. So you see, when rho gets closer to 1, then what happens to this queuing system is that most of the time everybody is busy, so you don't have these random assignments. Okay, everybody that arrives either sees all the machines busy or at most one machine is free. There won't be much choice, so the result is now not just dependent on this fluke particular choice, particular lambdas, okay, and we hope that this will give us some way of really dealing with the infinite matching model. Then also, if you look at the overloading reneging model, when the rate of arrivals starts to get close to the rate of processing, then your W becomes the total waiting time will get wait a minute, what am I trying to say here? Then less and less customers will renege, and you will get closer and closer to everybody being served, which again will be similar to the infinite matching thing. So maybe once we have a solution for the infinite matching model, we really also have a solution for the overloaded reneging model, okay, to calculate those Rijs under some conditions. I mean, this may well depend. I mean, we may need exponential assumptions, etc. Yeah, and of course, the infinite matching model doesn't have any distributions in it, so there's no exponential Poisson assumptions there. But there is the Bernoulli type assumption, the IID assumption. Okay, so again, maybe I should have really stressed that this is what I described is work of lots of people. So some of it I'm co-author, and some of it I was not involved. So that's okay. Thanks. Yeah.
They are not completely symmetrical. Is it true?
It is symmetric, yes.
But the matchings are established in the order the servers appear.
I described it as, I mean, I told the story as if it's the server that is moving along, but you can also have, that's another feature of this, you can also get, I mean, the way that, actually we have a paper on this in applied probability. So X will be the sort of word of leftover customers which the end server finds. Then you can have a process Y, it's a different process, it has a different state space, which is the leftover servers if you go with the customers. For every omega, for every sample point, it's the same matching.
Is it?
Yes. It's the matching is uniquely defined because it's between a pair. It's not immediately obvious, but it is, or maybe it is. I don't know. But that's the case. And then you could also have a process which, for a while, we thought was simpler, which would have up to the, when you just look at the first n, what is left over, how many are left over, both customers and servers. And that sort of is a little bit more complicated, but the cases we could solve, it looked like the steady state distribution was simpler. So
Okay, so you're trying to show that under those conditions that come from the graph and so on, that this thing is ergodic, and what that sort of means is the length of this X word of unmatched customers, that remains it doesn't grow to infinity, that it sort of remains bounded.
Well,
value or
y-
something.
well, I mean, it's a countable state space, but that
As the
it's
servers
that
coming
it's
one by
posi-
one, this word grows and blah blah blah. We want to just show that it doesn't blow up to infinity.
right.
That's sort of what under those conditions.
Yeah.
So it seems like a natural thing to do would be to try and think, is there any algorithm for matching the servers to the customers that makes the thing ergodic? So suppose I don't have to match the first thing guy from the left. As a server of type I arrives, I can find anybody in the present word to match him to. And I just want to do that in such a way that I manage to keep this word from growing
Mhm.
out, from getting too big.
There has to
Yes,
be-
and you think
accumulate over a large period of time and make your period of time large enough that the inequality is far enough away from one that you're safe. And then you could just choose an optimal policy over a large block of time and then start again.
Something like that. That's right. So there should be so it'd be interesting. They should to carefully see what policy, like the sort of Damon stripes, that will actually do all make it
Okay.
ergodic, right?
yes.
Because it all reminds me of like bin packing. We have
so-
first
so-
fit
so,
bin
but-
packing,
but-
best fit bin packing.
Uh-huh.
Some of these are ergodic and some are not. Depending
Yeah.
on the distribution.
Oh, okay. So some are ergodic and some are not.
And
Mhm.
I remember I worked with David Johnson very hard to show that online best fit bin packing was ergodic,
Mhm.
and it's
Okay,
only
I see.
just ergodic. I mean, it's so close. I mean, the simulate you can't really learn much from simulations, but in the end, we did it by Lyapunov functions. You said that somebody had done something on that problem with Lyapunov functions. It strikes me that maybe one just hasn't been clever enough in thinking of the right Lyapunov function yet. There ought to be a Lyapunov function that looks at this word and calculates some function in it, and you show that as each server arrives, the
I
expected
see,
value of
yeah.
this thing decreases. And then you can apply various lemmas that say that then means you've got an ergodic system.
Mm-hmm. That would be very.
I think that would be a way.
So yeah, at the moment we kind of are hoping that this product form will actually give us an explicit solution for this, okay? Which would be really, but if that is, but of course, yeah, if that's not the case, then one would still, it would look for, one should look for a proof of ergodicity that is not just for a particular particular model, but for all
I
of them.
can
I
tell
don't
you,
know.
you can always tell you if the thing is really ergodic, so there is a trivial Lyapunov function. It's just that we can't calculate it. It's the given the state of this word, the functional that I want to look at is the expected time for the queue to come down to 0. And as each server comes, the value of that actually has to decrease if the system is ergodic. Like you can't actually compute that, so you try and compute something different. Like suppose we have no more arriving customers, and we say to ourselves, what's the expected number of further servers that are going to have to come until we get rid of the present backlog? And that now again, that still might not be very easy to compute. So but you might be able to find some sort of approximation for it that would then work as the Lyapunov function for the original problem.
Why should it decrease with everyone that arrives?
Oh, well, if the system really is ergodic, then, the expected time for this queue to empty is this server plus the expected value where it goes. And so the difference between the left and right-hand side expected values have to be equal to -1. I mean, because you just had one server. I mean,
I see.
So you have it. I mean, I don't explain it very well, but there is that definitely is a Lyapunov function. Except you can't. I mean, that's like a new problem you can't solve. But
And that still works with the infinite sequences as well, right? I mean, it's
no,
not
you
a
don't-
queue
I
here.
like to think we don't worry about infinite sequences.
Yeah. Okay.
We just keep track, you say, of these
Yeah.
of unmatched words of customers.
Yeah. Right.
And anytime a server comes who can't match any of the ones we've got, then we have to start adding some more onto the end until he finds one that he can match. So you're right. So we have a nice description of the system, which is a word of unmatched customer types, which sort of comes and grows and
Yeah.
shrinks. And we want to make sure that it
Yeah.
doesn't grow and
Yeah. I
shrink.
can see. Yeah. Right. Yeah. Yeah. If it's ergodic.
Now, how can it
should
grow to
be less than
infinity? It's
one.
because it grows with some type of customer that we're getting faster than we can find
Yeah.
servers to match it. How could that?
Well, yeah, no. I mean, if if you don't have those inequalities that come out of the max flow, then
No,
of
but if
course
those,
it will
if
go to
those do
infinity.
hold, how could
Those inequalities would have to hold for any omniscient matching algorithm to work.
Yeah.
Yeah.
Another way to express this is, why is it you think that the first come, first serve algorithm isn't losing anything
That's
by
right.
virtue of having to restrict itself to certain matchings?
I see, yeah.
And in the case of input queued switches, you do lose stuff if you restrict yourself
Right.
to head of line, to the person at the head of the line. But
That's right. It seems sort of, and certainly in bin packing problems, where an omniscient person could obviously pack all these things, but because you're doing it online, doing first fit or something, you actually lose the day you lose something. So it seems rather odd that this first fit sort of matching here doesn't lose anything. Are people really convinced that's the case? I mean, no one's found it.
I don't know. I mean,
How
it's
much work has
it's
there been on doing simulations of different systems? And seeing-
not that much. Yeah. No, I think we sort of started
I
this.
think you have
I'm
to look
not
quite
sure.
hard to find examples, say in online bin packing, where you do lose. And it might, but it might be a little bit more luck. Look at.
I'm not really aware of looking at these infinite matchings
But
by
if your
anybody
service-
else. Maybe it is. It has been done. I don't know.
If your service time only depends on the server, why should it matter which customer it picks up? Why should you lose?
because
Oh.
if the server chooses a customer of the wrong sort, then that may be precluding some actions from a future server.
That's right. You sort of, ideally each server, in some sort of wants to be doing the customers that other people don't want to do. I mean, but it's a very difficult notion because it's all tied up in the graph. But yeah, no, it's an intriguing problem. Yeah, I like it.
Okay. Thanks.